All right, now we're going to look at spherical coordinates. And so the same thing's going to happen. We're going to have three parameters that represent something within three-dimensional space. Again, I'm going to start with my graph here, and we'll use a graphical representation to look at our spherical coordinates. And so what we're going to do is we're going to say that some point in space can be represented by an ordered triplet of rho, phi, and theta. And what we're going to notice is one, rho is the distance from the origin to the point P. And so that means rho is going to be greater than or equal to 0. 2, phi is the angle that if we call the origin O, then the vector from the origin to P makes with the positive z-axis. And so phi is going to be trapped between 0 and pi. And then theta is the angle from cylindrical coordinates. And theta, as within cylindrical coordinates, is between 0 and 2 pi. So let's draw this and get a feel for what's going on, and then make some relationships here. And as everyone knows in class, I completely messed up these relationships by babbling over them. But we fixed it all in the end because some people were very, very observant on my bad notation. All right, so here's the y-axis. There is the x-axis. And there's our friend, the z-axis. So there's z, there's y, and there's x. And we're going to have some point P. That's going to be represented by rho, phi, and theta. Almost like phi, phi, thumb, rho, phi, and theta. And we're going to draw some vectors here. So here's the vector 2 phi, or 2p, from the origin to P. And let's drop down some lines here to talk about where we come onto the plane here. We'll make some related triangle relationships here between the different coordinate systems. All right, so first off, this is the x-coordinate. I think I can get rid of my grid now for a little bit. This is the y coordinate, and this is the z coordinate in Cartesian. In polar, this is theta, and this vector is r. And then within spherical coordinates, this is length is rho, and this angle here from the z-axis to rho is phi. So we can see every coordinate system stacked on top of it. So the first thing we're going to look at is how r relates back to rho. So this projected downwards here is the co-angle to rho. So if I project on to z, if I project onto the z-axis, this projection here, right, the shadow of rho onto z, well, that's the adjacent to the angle, so that's the cosine. So I guess we could say z is rho cosine phi. And that is the projection from rho to z. Well, this r vector is perpendicular to z, and so this is the co-function down here. And so r itself, r is equal to rho sine phi. And then if we look at how x relates back to the polar coordinates, x is r cosine theta, and y is r sine theta. So x, I can replace r with rho sine phi, and for y, I can replace r with rho sine phi. And we have our relationships between the Cartesian coordinates and our spherical coordinates. And so if we put these together, if we put kind of a list of, well, x from Cartesian or from spherical to Cartesian, we'll have rho sine phi cosine theta. Y is going to equal rho sine phi sine theta. And z is going to be rho cosine phi. And so we have our coordinate transforms. And if we go the other way, rho is x squared plus y squared plus z squared. And that's the same as r squared plus z squared. So we have the beginning of spherical elements. Let's look at a differential element of volume in this coordinate system. So if I have some radial component that's going to have a differential on it, so I'm having a sphere I'm going to draw my sphere elements. Trying to think. That's spherical out this way. Spherical down this axis. And spherical down this axis. And so what I want to do is I want to look at some volume element. I want to look at some volume element projected outward. So I'm going to have some radial component come out to the edge of my sphere, along with some other radial components here. Let me, there, and here. And if I arch across here, and I come across here, to this element. And so I have some volume element within this space in spherical coordinates. And so the volume element I need to look at all of the pieces that make up this element. And so I have this running on an inner sphere. All right, so we have curved surfaces here, and a curved surface here on this outer element. And so I have a distance along the length of this element from here to here. That distance is delta rho. Because this element here is moving in the radial direction. All of these elements have a delta rho distance on them. Now the arc that's coming down from here in the inner sphere here, this arc is moving across in this arc length that it creates here, this inner arc length here. So I'll point right to here. Well, that's a distance rho times whatever I'm changing in phi. The arc length that scrapes out is rho times phi. Now, depending where I am with phi, the arc length that comes across with this component in the polar coordinates, if I'm higher up, the projection on the polar coordinates, that theta, doesn't sweep out as much. And if I'm lower down, this arc here sweeps out more. And so that component piece is rho sine phi delta theta. Because we need the projection of how steep this is. If it's a really tight angle, the part that's projecting down into the polar coordinates will be a smaller projection. And if I'm at a really low angle, it'll be a larger projection. And so I have three volume components that come together to give me this volume element. And so my differential of volume is going to have a rho sine phi, and then a delta rho, a delta phi, and a delta theta. And if I combine these together, then I'm going to get a rho squared sine phi dr d phi d theta. And we can always talk ourselves back through how to create this by summing up elements, right? It's the same type of argument. My integral over some region with some function is going to be times the differential for the volume. That function has to be in the same coordinate system as the differential. So if my function is in with rho phi theta, then my differential is going to pick up rho squared dr d phi d theta. And so this would be our integration within spherical coordinates. Our process is going to be very, very similar to what it has been in finding the limits of integration. So what I'm going to do is I'm going to pause the video here. I'm going to put this up for our coordinate transforms, and then I'm going to talk about finding the limits of integration in the next video.